Welcome, Code Slingers. In this tutorial, we're going to cover the queue data structure. A queue is a collection that allows you to enqueue or add elements and dequeue or remove them in the same order as they were added. Imagine this crossword is our queue, and the gentlemen walking in on it are our elements. So there's John, Richard, Paul, and George. So since John was the first one to get into the queue, he will also be the first one to get out, and then wait a second, what just happened here? Okay. Another good visualization is that of a fast food drive-thru, where the first car to pull up will be the first one to order, the first one to get served, and then the next, and the next, and the next, and so on. In other words, the first element to get in will be the first one to get out, thus following a first in, first out order, or FIFO, or FIFO. So how is this behavior accomplished under the hood? Well, it turns out that a queue is built on top of a linked list, except you always have a reference to the head and the tail of the list. That is the first and last elements of the list respectively. When you add a new element to the queue, you do so from the rear or the tail of the list. In other words, the newly added element becomes the new tail. However, removal always happens at the front of the list, so you always remove the head element and the next element over becomes the new head. This is how you ensure that the elements are always removed in the same order as they were added. Let's now talk real quick about the queue's complexities. Since we know the exact location to queue or add, and that is at the rear of the queue, its time and space complexity are both constant or big O of 1. Likewise, we know the exact location where to dequeue or remove, and that is at the front of the queue. Therefore, our complexity is constant for that as well. There's also a peaking function, which we'll cover in a minute, and it also happens only at the front of the queue. Therefore, its time and space complexities are also big O of 1. Searching would have a linear time complexity or big O of n, assuming worst case scenario would have to traverse the entire queue to find the value we're searching for. But since we'll only be holding one value, its space complexity will be constant or big O of 1. Finally, storing would take both a linear time and space complexity, or big O of n, since we'll need to traverse the whole queue and store every value as we go. Let's now dive into our coding example. First, I'll define a queue of integers, which in Java is done by leveraging the linked list class. Once my queue has been defined, I'll go ahead and add some items to it. In Java, you can add items to a queue by using either the .add or .offer functions. Just want you to keep that in mind. Now that my queue has been populated, I'm going to remove its elements one by one and print them to the console. For that, I'll use a while loop. And while queue is not empty, I'm going to declare a variable to hold the value being dequeued. And in Java, to dequeue, you use the .poll function. And I'm going to print that value to the console. So when I run this, I see that indeed my items are dequeued or removed in the same order as they were added. You can also remove items with the .remove function. So let me show that as well. And run that and we get the same result. Let's now talk about the peek command. Let's say that you want to know what value is at the front of the queue without actually removing it from it. For that, you use the .peek function. So I'll print out a line that says the next item on the queue is, and then do a .peek. And here we see that the value is accessed without being removed. Cover some queue trivia. Some differences between a queue and a linked list. As we mentioned earlier, a queue is built on top of a linked list. However, a queue holds a strict first in, first out order. You can only add from the rear of the queue and remove from the front or head, whereas a linked list allows you to add elements at the end, in the middle, or in the front of the list, and therefore order of insertion in a linked list is not as important. Another item to keep in mind is that a queue always has a reference to the head and the tail elements, therefore making adding and removing elements a constant complexity or big O of 1, whereas a linked list only has a reference to its head element, but it may or may not have a reference to the tail, and therefore adding or removing on a linked list may have a linear complexity or big O of n. Array list keeps its order of insertion. Can I use that instead? Excellent question. An array list does indeed hold its order of insertion, but its remove function has a linear complexity or big O of n, versus a queue having a removal complexity of big O of 1. That is because an array list allows you to remove any element from the list, whereas a queue, as mentioned earlier, only removes from the front, and therefore follows a strict first in, first out order. These are actually the key differences between a queue and what is a priority queue? A priority queue is a queue with weight or prioritized elements, meaning that some of the elements hold higher priorities than others and need to be executed first, even though they're not at the front of the queue. Priority queues are kind of rare and a little bit beyond the scope of this tutorial, but let me know in the comment section if you'd like to see an in-depth tutorial for priority queues as well. And I think that settles it. So hopefully this video has provided a better understanding on queues and their usage. So please don't forget to like and subscribe, but most importantly, share this video so there can be more and more code slingers like us out there. And see you next time.